This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
So just needed to be asked again. Fair enough. Okay, I'll resume where we were this morning. I was struggling to explain to you the rationale behind the concept of noise equivalent bandwidth, and I'll try again with that, having had a bit of lunch and a bit of a rest. The whole concept is that we have a situation where noise can be transmitted through a filtering component, whether it be a deliberate filter or simply the bandwidth of the system that we are using. For example, it might be the band limiting of a typical op-amp. Now that band limiting then will mean that signals get passed to some extent and get rejected to some extent. And here's a low-pass filter that we're all familiar with, first-order low-pass filter, where we'll get good transmission in the bandwidth, which is indexed by the 3 dB point, or the 1 0.707 value of transmission, and thereafter signals get attenuated at higher frequencies. So over here, signals are gradually becoming attenuated. However, noise being all pervasive, particularly if it's white noise, where the level is constant over infinite bandwidth, theoretically, we would have, hello there, we would have better transmission of noise than we might expect, like this. Just reduce that a little bit if I can. But the noise is going to come through. Now, when I wanted to demonstrate feedback for oscillation and instability, I couldn't do it. Now I've got nothing but. That's altering the recording volume, but not this one. Yeah. Did you ever have one of those days? I might just put that off and rely on the desk mic here instead. You guys are smiling here. Did you do this? Why not? Would have been a good gag. Thank you. Okay, I'll stand over here so I'm close to this mic. So what I'm rabbiting on about here is that we'll get noise through in this region, and the whole idea is that if you can regard that noise that's getting above the bandwidth, you get a kind of a profile here that you might regard as, let's think, maybe an analogy is a bulwark against sand down at the beach or something like that. You know how normally you get the sand coming down to the water line like this. Here's the water down here on this side, and there's the hill as you approach is up here. So as you get to the water's edge, the beach comes down fairly flat. Sometimes to protect against erosion, they put in bulwarks of timber or something like that, make a frame against erosion. So a vertical frame here. My question is, how much sand do you have to, where do you have to put this bulwark so that the sand that you take from this side and shovel over the top gives you a flat edge here? Alright, is that a good analogy? Yeah? Okay, so we're shifting the bulwark, if we can do it, to a point where the sand that we shovel in from this side down to the water line, we can throw over the top and make a flat edge here. So it can take a run off here and dive in, splat. Yeah? Alright? Yep.
Wait, are you saying that, like, even though you've passed this noisy signal through this filter, the part that you want, the frequencies that you do want, they still have noise on top?
Yes, there's still going to be noise present.
But are you saying that, like, the fact that you cut off, like, the noisy signal that's, like, in the upper frequencies, that somehow affects?
Yeah, you'll still hear it in an audio system, you'll still see it in a video system. The noise will still be present. It will be attenuated, but because it's wide bandwidth, and unlike signals like my boring voice, which is band limit in itself, my voice doesn't extend out to infinity frequency, although some might think so. It tapers out. Yeah? However, the noise doesn't taper out of its own accord. Well, it does, and as I said this morning, that's in the vein of terahertz, way high frequencies. Yeah? So that is an ever-present noise that will contaminate signal. Yep. And if we can deal with that somehow, or know how to treat it, that's good. We can characterise it, and we can characterise the filtering process, the way it treats noise, by thinking of a noise equivalent bandwidth as if it was a square flat filter. And the way to do that is imagine how much gets above the signal bandwidth, This is F0, the nominal 3 dB point that we use for signals. And we say, okay, how do we adjust that to account for noise, right, at high frequencies? How can we pack that noise in our mind's eye at low frequencies? What do we have to do to make a dumb brick wall filter, conceptually? And the idea behind that is to take this area under here, which surprisingly does converge to a tractable value, yeah? And we stuff it in the top here, okay? Shovel it in, if you like. If we shovel sand over, how much sand how far does this have to come over so we get a flat top here? Good?
I was wondering how did you buy 1.57?
I didn't. A lot of clever people did with clever integrations. And I can refer you to the text that you'll see this in is Ed Cherry from Monash and Darryl Hooper, who was here at Melbourne before he went to General Electric in England, I think, and came back to work at La Trobe University here. So they're Melbourne guys, and they wrote a very seminal book in ATEC called it's abbreviated to ADLPAD, Low Pass Amplifier Design was the last bit. I can give you the citation if you like, but it's been derived, and they're called noise integrals. And following on from Sian's questions this morning, they also derive for higher order filters and also for the bandpass filter that has a low pass, a low frequency breakpoint as well as the high one. Yeah, so it's been done, and it's possible, and we don't have time to do it here right now. But it's an integration. Yeah, so it's just saying, just equating this area here and that area here, and making this the integration limits here.
What does this number actually tell you about the behaviour of the system? A little bit clear about what it actually tells you.
What it tells you is that there's more noise than you would expect getting through a system. There's more noise than you would expect from the nominal signal bandwidth. Yep. Right, and how do we account for that? Yep. We can't use the same index that we do for sine waves. And when we have sine waves, we have this very kind scenario where in this transfer function of this first order system, when the real part and the imaginary part of the denominator are equal, then the magnitude is the square root of real part squared plus imaginary part squared, and that's where this 1 on root 2 comes from, right? If you're using other than sine waves in a system, suppose it becomes a triangular wave when things reach their slew rate, as we saw in the lab, then this index here somewhat goes to pot a little bit. It's no longer valid. It's valid for sine waves, but not for other waves necessarily. John, is that just a scratch? Okay.
So I'm just wondering whether brick wall cookers, is that saying from that point, anything from under that point
goes to zero here. Yeah.
Past that point.
It's a fudge factor to say, let's set this point here so that we can say that anything before it's a 1, anything after it's a complete 0.
And that's for noise.
It's a noise equivalent bandwidth. Yeah, equivalent. Yep. Just to say, let's make this area here the same as that area there, where do we have to put this line so that that's true? Yeah? I mean, it's going to be really hard to keep shifting the bulwark with the sand, isn't it? Yeah. So, I mean, that's just not a really good analogy. I can't think of anything better right now.
So it's just saying that's the point where the areas match, and that's the operation essentially of how much of the point. But after that point, it's not like we have
Zero.
The system.
Zero. Whereas in reality, if we use the nominal signal bandwidth, f sub naught here, there would be signal coming out, attenuated, but probably the signal source will be dying off as well.
Yeah.
Yeah?
The
Yeah.
ratio.
All right. Now, the reason why I'm bringing this up here is that if you want to understand this stuff and you want to deal with, if you want to deal with the sorts of things that you see, that you will have already seen in the data sheets for op-amps, you get these awful diagrams that look like voodoo and squash spiders and so on. You know, it's just, when you first see it, it's, what's this about? It's crazy. And oddball graphs with oddball units on them, square root of hertz. What's that about? Who would have heard of that? But it turns out that if you go slowly through it, you can understand this. Yeah. In fact, the exam question I put on this last year, which I'll give you a look at today, students did quite well with, and some of them almost understood it. Okay, so why are we doing this? Well, once again, it's because the signals that you'll be dealing with, the biopotentials, are really darn small, and this noise can creep in to give you problems with signal contamination. Yeah? Okay. It's not just because I like it. Yeah, I know I'm a bit weird. Okay, so there's a couple of tricky concepts, and that's one of the trickiest ones. The other one is this equation that we talked about before. If you can get a handle on this, then you're halfway home. And the reality is that the manufacturers will give you a white noise level for white noise that's generated in the op-amp, and they'll usually tell you a corner frequency where there's departure to a 1 on F profile that gets higher as frequency goes lower. Yeah, low frequency noise. Now this is also seen in a lot of biological processes too, by the way. In devices, electronic devices, it's usually due to surface effects and imperfections in biological processes and natural things like some climate stuff and so on and so forth. It's not understood, but a lot of systems correspond to this kind of frequency behaviour. Yeah.
Are the upper and lower frequencies on that graph the same for pink noise and white noise?
No, what we're actually saying here is that if we take a slice, if we have a particular bandwidth of interest, we might have a device that works up here, say, this is the low end of the bandwidth and this is the high end of the bandwidth. Then calculation for that's a cinch. We just take the high minus low and multiply by the white noise level. And that's what you see here. There's E and W multiplying by some junk here, which we just ignore for the moment, and some stuff here, which is obviously a bandwidth, high minus low, multiplied by a level, voltage level. So that's a block, if you like, if I can sketch a block here, you know, arbitrary high and low frequencies, where we can ignore the pink line because this is a log scale here, so as we go down in magnitude, this is kind of disappearing, so I'll happily just ignore that. Alright, so if we're looking at a low frequency process where the 1 on F part is prevalent, then we could set maybe we'll put FL here and FH here, and then we just have to work out the area under this trapezoid to characterise the amount of noise present, because the white noise is logarithmically that far below that we can just ignore it, yeah? Alright, now, the problem can be when we're straddling those 2 points. So then we need to take a tricky bit here that's a little bit hard to unravel, but we can unpack it if we can be bothered to fight it out. And we need to include also the bit that's above this corner frequency. So there'll be if I'm saying this is FH here, and this is FL here, clearly there's a bit of 1 on FE bit on this side, and mostly the white noise part on this side. Yeah? So I've got a region that's sort of blah blah blah, like that we need to calculate. And the way we can calculate it is with this corrupted version of what we might have had before for 1 on F that I described this morning. That's pretty straightforward, and it's characterised by coefficients here. If we equate the point where the white noise and the 1 on F noise are equal, then we can eliminate this coefficient and recast it in the form where there's just this so-called noise corner frequency, which is the frequency at which those 2, 1 on F and white noise, are equal. Yeah? Good? Now, happy with the concept, maybe not the mechanics of it all, but you're clever people, I'm sure you can work that out if I put it on an exam paper. No. Now that I have your attention, though, with that 4-letter word, basically it's a way of compacting it into 2 parameters, yeah? And you only have to bring in your high frequency end and your low frequency end, and the manufacturer tells you, if you're lucky, this and that. Otherwise you might have to, for some manufacturers you might have to make a wag guess, yeah, which is tough. And let me say, it's a lot easier if you have the units in volts squared per hertz to make that projection, even though it's an oddball. Yeah. If you get it in mean square rather than RMS values, it's easier to make that projection from a graph, like here, to the white noise level. The white noise level we can pull out here quite happily, can't we? Yeah. So if I asked you what's the white noise floor level for current, you'd be able to tell me quick as a flash, wouldn't you? It's... Sorry? Five three what? Okay, picoamps per square root. You're saying it's 5, yeah? Okay, yeah. And be careful again, because you've got to make sure you're not looking at a log graph. But we're not this time. This is log, that's linear, isn't it? Yeah? Be careful of that interpolation of logs that we talked about this morning. Alright, now I haven't talked about amplitude distributions. Many of the noise processes we see are Gaussian, normal. What else did I need to tell you about here? Have a look at the examples in the slab of notes that I put on LMS for resistors and noise. There's worked examples in that for you to try out, to get your head around what happens in these noise scenarios. Are there any other questions on noise equivalent bandwidth? Do you think you got even a fuzzy, hazy idea of what that might be about? Yeah? Who reckons they've got it? Thank you. Thanks. It's embarrassing, isn't it, when you get a grip on it. Okay. You get typecast then a little bit. I want to talk to you about diodes again now, because when you've got diodes with DC current flowing, then there are conduction processes over potential barriers, and we're told that when the charge carriers move over a potential barrier, they they make a little noise each. And here you see it, this is from Graham Meyer, I didn't accredit that here, but basically it's a diagram from Bob Meyer, who used to work here in electrical engineering, another seminal world authority on noise. And this is the sort of noise that you get due to a DC current flowing in a diode. Now, we talked about excess current in resistors. That gives a 1 on F type noise profile. This is a more white noise profile. And once again, you get spot noises, spot noise values, but the spot noise value is going to be fairly constant predictor over the frequency range, so all you need to do is multiply that spot noise value by the bandwidth to get the oomph of the noise. Yeah, the noise power, if you like. So this is spot noise. I've called it subscript S. I mean, this lowercase I is a spot noise. The N means it's just general noise. The subscript S I'm using here to indicate shot noise contribution, and it's proportional to electronic charge and the DC current flowing. So more DC current, more shot noise present.
I'm a little bit confused between spot noise and
Yeah.
shot noise.
Thanks.
What's the difference?
The difference is entirely. Spot noise is just a profile, right? It's a spot noise is a notion of a noise, be it from shot noise, from thermal noise, and other noise processes at a specific frequency. So we got frequency going up in frequency here, and the noise is going up and down, and at this particular frequency, this spot, it's got a particular value, and it's normalised to 1 Hz bandwidth. Yeah, is that right? Whereas shot noise is called shot noise because it was likened to lead shot falling on a floor. Yeah, you can imagine. You know what I mean by lead shot? Yeah, shotgun pellets made out of lead, tiny little pellets. Imagine lead pellets, spherical pellets in a casing that you put in a gun, yeah? And there's a bunch of them inside a little cartridge, and they're, how big are they? Who knows? Sorry? Oh, no, very tiny. Oh, yeah, absolutely, like even smaller than pebbles. A bit bigger than sprinkles.
Like little styrofoam balls.
Smaller than that, tiny, really tiny. Does it matter? Yeah, good question. Probably if you're getting shot by it. But anyway, that lead shot falling on a floor makes it sound like rain on a tin roof. Yeah. Okay. So the analogy here is, for loudness, the current, the ID here, the current in the diode, ID, the analogy to that in the rain on a tin roof scenario is the flow rate. Yeah? The electronic charge is analogous to the size of the raindrop. but we have uniform raindrops because Q is 1.602 to the 10 to the minus 19, isn't it? Yeah? Is that right? Electronic charge? Yeah? Okay. So that doesn't change. You have regular raindrops in this analogy. The flow rate can change though, and so the noise changes. What's the analogy to the bandwidth, folks? What's analogous to the bandwidth in my thought bubble here?
Size of the roof.
Well done. Yeah. Bigger roof, more noise. Collects more rain. And similar sort of sound. There's a granularity to it. Yeah? Right? And you get that little bit of granularity when you hear rain on a tin roof. Cool? Okay. Same sort of story. We've got these constants that you can use with another noise process. There's a flicker noise due to imperfections thought to be due to imperfections in fabrication of diodes that gives a 1 on F profile again. That sort of thing comes up this way for you. And there's an index that depends on the actual imperfection. It's arbitrary, but it's typically a F to the minus 1 type of profile nonetheless, and usually due to the first power of current, but no big deal there. Alright, so what's this all about? Well, we like to draw these circuit models of electronic components, and for a resistor we would have we can have a series voltage associated with a physical resistance. So this is meant to be a diode here. There will be, due to the component pigtails, you've seen diodes, they're just like resistors, the ones that we have in the lab. So there's some resistance to where the action is inside the diode. So the leads themselves, they're like wires. So they've got some resistance, maybe a fraction of an ohm, but it's a resistance nonetheless. And there's also conduction pathway to where the action's going on in the diode, the junction itself. So it's what they call a bulk resistance. So that's a real resistance, and it's present all the time. And there will be noise going on in that, even if we've got nothing connected to it. If it's not at absolute zero, there will be some thermal noise associated with that resistance. Yeah. The other resistor that we see here is an incremental resistor modelling the difference between modelling the relationship between current and voltage in the diode from an AC sense. So, and that's proportional to the DC current that flows. That's all very confusing, and we haven't really treated that as well as I would have liked, but suffice it to say it's a relationship for small signals, and it depends on the DC current that flows. It's like the water level of the analogy of making waves on top of water, yeah? You have to have some water happening before you can make waves on it. There's a DC current supplied to do that, and it just turns out that the relationship of current and voltage, or potential and flow, in that tiny wave you're making on the surface is proportional by this argument here. But the main point is that when there's no current, that's off, that resistor disappears, or it becomes extremely high. Yep. Becomes lower as the current increases. Yeah. And the constant of proportionality is kind of obscured by KT on Q, but that's what we know as VT, or 25 millivolts at normal room temperature, 17 degrees. And some people call it 26 millivolts because they're thinking of hotter temperatures, 25 degrees Celsius. But basically, if you use 25 millivolts, that's a happy figure because it's easy to manipulate arithmetically. Now, so there'll be a shock noise current in the diode. That's due to the current that flows, and there's also a thermal noise, tiny thermal noise in the resistor. So that's the noise processes of this diode, and there can be a flicker component here depending on how bad the production is. In other words, that's K value, but we won't get involved in that too much, if at all. Another noise process that doesn't have a normal amplitude distribution, it's like a telegraph signal, and this is serious noise behaviour with device defect, materials defect, where carriers jump between two specific levels. And I managed to get, I bought my brother's hi-fi amplifier from him because he had it to Ansell's workshop so often to try and get rid of popcorn noise in one channel. I bought it from him because I thought, I've got an example of popcorn noise. Yeah. So he wanted to get rid of it, and I thought this is a good example. I won't bring it in to show you, but because it's only ever so often, you get little pop, pop, pop from one side. But it's jumping between two levels, also called telegraph noise, and you get this two-horned amplitude distribution. That's just a peculiarity we won't worry about. I just put it in there for sake of completeness. Here's something for you to do now. It should be on LMS, I think. It was there last week. Is that, yeah, still ringing a bit. Yeah. Has everybody got enough of the question there, or maybe too much of the question? So what would be the first thing you can do? Figure out the DC current that flows. Who's got a value? How are we going to work this out, folks? We'll say that when the diode is operating, 0.7 volts here, yeah? Agreed? Yeah? So the current I will be 10 minus 0.7 over 20 k ohms. Correct? About half a milliamp. Who wants to give me a more exact value for what it's listed? 5 micro. Okay. That's what I got. Okay, so we can do a diode model then. Would you agree? Right, focuses. Because we're not given a value for that little bulk resistance RS, we can ignore it. Because there's no information that might help us with flicker noise, we can ignore that. And so we're left with RD, which will be the value of BT on ID, 25 millivolts divided by 0.467, whatever. Agreed? All our focuses? Oh, it's hunting around, isn't it?
The VT
VT is KT on Q. The volt equivalent of temperature. In first year I had a girlfriend called KT who was always punctual. So it was easy for me to remember. KT on Q.
What's our value of Q in this case?
1.602 times 10 to the minus 19.
Very
amps. Coulombs, isn't it?
Coulombs, yes.
Right.
And they're all constant of the temperature.
Yeah. Yeah, the temperature's a variable. Yeah. Good.
Plus temperature is model. You would tell the temperature
Yeah, but if we say 17 degrees Celsius, which is about today, isn't it? Then we end up with 25 millivolts, I think. Yeah. You'll see a lot of people get bolted on to 26 millivolts. And that might be a reasonable thing to do because inside
cases like up there, when it's cooking, that thing up there with electronics in it's going to be a lot hotter than ambient room temperature. So maybe 26 millivolts isn't such a bad number after all. But yeah, okay. So, sorry. K, that K is Boltzmann's constant. So 1.381 times 10 to the minus 23 joules per Kelvin. I could remember one of those, I could try to remember Boltzmann's constant or the electronic charge, but never both. Except with KT's help, of course. And what you can try and remember, folks, is VT is equal to temperature in kelvins over 11,600. Yeah, that I could remember. Because if you remember that number, you can, and you remember either K or Q, you can work out the other one. Yep. Good. Okay, that's the diode model. Now, when we also have to account for the resistor as well, because the resistor ain't just a resistor anymore. It's got thermal noise associated with it. So we have to account for that. So our resistor is resistor R. Oh, I haven't put in here what the shock noise is yet, have I? So I squared was 2Q times ID. So I'll get you guys to figure that one out. So this is IS squared here, I subscript S for Schottky. And over here we've got R, which was 20 k ohms, and it's still 20 k ohms. And IT squared, the thermal noise. Maybe I skipped over that earlier on. Thermal noise here, where it's and you can put in a subscript T for thermal. So we could say that thermal noise squared is 4kTr. And what that means is that if we render it into a form where it's a current generator in parallel with resistance rather than a voltage generator in series, we'll end up with 4kT on R. Just take a minute to work that one out, I think, but it all hangs true. This is the same K, yeah, Boltzmann's constant. So pardon?
It's a little K on that, just like this one.
Yeah. Yeah, it's a little K. True. It shouldn't have done. Shouldn't have.
if it was my writing, it wasn't meant to be a capital K. Little k. We probably need to, I think it, doesn't it have a hat or something? Boltzmann's constant. Doesn't matter. Symbols. What a headache. Where was I? I don't know why it has to keep doing that. It does. So we'll call that IT now for thermal noise, just to distinguish it from.
Do you want to solve for both the voltage and the current for thermal noise? Or?
No, just the current, because it might not be apparent what I'm driving at here is that when we do an AC equivalent circuit, we imagine that the voltage source that's driving this is in the background. So we kill this off by making a short circuit. What that means is that this resistor becomes in parallel with the diode, which means that what we're going to be doing is we'll be hooking those two together. Yeah? Does that make any sense?
If you look at them both independently, they're in series.
Well, this is a ground point, so effectively, from an AC point of view, the resistor and the diode are in parallel with each other. Yeah? Yeah? So we've got a model for this and a model for that. They're both joined at this point here. So this is the point here, and ground's at the other end.
Yeah, it's parallel.
So we're putting them both together now, and we can sum those two currents on a mean square basis, and we'll have a resistor that's the parallel sum of these two resistances when it's in operation.
Because current adds.
Mm.
Okay, current adds in parallel.
Mm.
Explain why it's in parallel.
Okay, it's simply because from an AC sense, the DC thing that provides the 10 volts looks like a short circuit internally. Yeah, let's say this is the device, the DC power supply that's providing 10 volts. An ideal source. Its internal resistance is 0. Yeah? So any equivalent AC sources that are appearing here will penetrate that directly. Any currents that appear here will penetrate that directly. Yes? You seem suspicious. Just doubtful? Yeah, do that.
Any other good questions? Why aren't we having a break? What did you say? So what happens next? Consolidate the two resistances together and the two currents together and find out what voltage arises as a consequence. Yeah? Can we put the two current sources into one? We'll call it IS squared plus IT squared. And now I'll just use the overarching line in here, and I'll back that off so you can actually see it. And then we might be able to measure some spot noise. Power. And then we've got to figure out how the bandwidth affects that. So, will we work all the way through it, or do you just want me to give you the answer and let you work through it? All the way through. Bring it out. Okay. Go for it then. Anyone got a value for this? The sum of the two? Well, did anyone get a value for the shock noise here, for starters? Yeah. 1.5 times 10 to the minus 22. And the units were squared. Per hertz, yeah, not per square root of hertz. Good. Yeah, it's terrible. Alright. And what about this one over here? Anybody got that thermal noise? 8.2? Okay. And the units are? Amp squared per hertz squared. Yep. Alright, so when it comes to this bit here, would I be in trouble if I just neglected that? If we just drop that and we just say it's mostly the shock noise? Yeah? So that if we bring this down to earth, then it's square root of 1.5. 1.2 is it? Something?
amp square root of hertz. Agreed? Seen it all before? Yep. Huh? Well, I think we're almost there, aren't we? What remains to be done? So we can neglect the thermal noise. We can neglect the thermal noise of the resistor because it's smaller than the shock noise of the diode, and we can probably ignore the resistor itself because it's much larger than the incremental resistance RD of the diode. Right, so that works out to be, what do we have for that? It's 50 ohms or something, wasn't it? Sorry? 50.7. Can I call it 54? Alright. So if that current flows through that resistance, then we'll get an EN value of the product. So it's, I don't know, 70 times 10 to the whatever. Alright, well, that'll give us an EN value. And that's a spot noise again, yeah? It's one spot in the frequency range, which is going to be constant, and a constant indicator because the processes are white. Both the shock noise and the thermal noise are white in spectrum. So then all we need to do is multiply by the bandwidth. But don't forget, it will have to be the square root of the bandwidth, because ET squared is 4kTRB, so ET is square root of 4kTRB. Did that fit on the page? Yes, just. So my answer ultimately, do you want it now? Because we're pretty close. The actual noise over the bandwidth I got as 0.21 microvolts. Right. After all that, what a letdown.
It was 100 kilohertz, wasn't it? So you multiply by the square root of that. Multiply this by the square root. Oh, sorry, I'll be a bit more clear. You multiply this spot noise voltage by that square root of that bandwidth.
Oh, that's okay, so it's like, okay, it's a bit different, okay, so to get the capital E then, you have to divide by,
Multiply by the bandwidth.
multiply by bandwidth, okay, so you have this value here.
Yeah, yeah.
That's what
We all good? Square root of. Yeah. So it's still a pretty tiny value, isn't it? But if we're talking about EEG signals, for example, that's in the order of electroencephalography type signals, isn't it? Good. Subsidiary question might be, what value of capacitor would you put across this to give you a noise equivalent bandwidth of 100 kilohertz? I don't know what the answer is at the moment. I haven't worked it out. But I suppose that's a question one could ask. Any questions on it at the moment?
I'm thinking of units now, the IS, like I know it's given in the section.
This one here?
Yeah, the units.
Unit? Look at that.
Because you the like coulombs times X, and you get a squared on that.
Yeah, coulombs multiplied by coulombs per second, isn't it? Yeah. And don't forget this is per hertz, so this has got the dimensions of 1 on time. Yeah. Coulomb squared, yeah. Coulomb squared per second. And then this is per seconds in the hertz. Yeah. It works. I think it's dimensionally correct. It's a good question. Yeah. Well, good. I like that. Can we press on then, or any other great questions? Uh-huh.
isn't it? I have to blank that first. Oh, okay, right. This might be just a little bit, we won't bother too much with this, I'll just put it in, we're not going to worry about burst noise here, but I'll just make a flying mention of it. This is a profile that kind of demonstrates that you can use log plots for rather than frequency response transmission plots, in other words. Here it's, this is very old when I did it, but it's basically plotting white noise from a particular diode with flicker noise and also this business of burst noise, which has a different profile. Part of the question asks what the flicker noise regions are, and they're basically where the flicker noise exceeds everything else. So there's a region here, and there's a region here, where flicker noise is greater than everything else, and this would be the burst noise region, and then there's a white noise region over here. And the usefulness of the graph, the log plot graph here, is that you can make quick changes between amps per square root of hertz and amps squared per hertz. So just by, I've done a sort of a rough indication of changing from amps squared per hertz to amps per root of hertz in blue, the other one in black, whatever. Okay, now I'll just talk a little bit about op-amps noise without going into it in great depth. We'll just touch on it and we'll follow up with the heavy-duty questions. But similar to what we talked about with op-amps and the DC non-ideal behaviour, just bring the lights up for you guys. We can model the noise processes that occur in op-amps by aggregating them into equivalent generators. So you'll appreciate that there's a lot of components in an op-amp, and rather than deal with all those components separately, we can lump them all together and say we can put these generators into, say, as if we had a noiseless op-amp. What would it take to produce the noise that we actually see at the output of the real op-amp, which is the big triangle here? So we model the noise in terms of current and voltage at input. Yeah? So it's lumping all the bits and pieces that go to make noise inside here, just aggregating it all into all those currents that, like we just did with two components, put all those noise processes together and lump them all out in the input, as if. You get the idea? Just to model the behaviour, so that we, I guess you can say, we think of the op-amp with its gain, we see some noise at the output here, we look back down the telescope as if it's a microscope to see what would give rise to those behaviours at output if we divided by the gain. Yeah? And why do we do that? Well, what happens when we hook up components here? Imagine there's a noise current flowing through a resistor. That'll produce a voltage. That voltage will be amplified by the ordinary processes of the op-amp when it's made into an amplifier circuit. Yeah? So the very act of hooking a resistor here that's meant to provide some gain will introduce a pathway for a noise current to produce a voltage that then gets amplified along with everything else, including the signal that we seem to have forgotten about for the time being, but that's what we're here for, amplifying a signal, yet inadvertently going to amplify that noise as well, regrettably. So, typical op-amp noise voltages have a white noise floor value and a pink noise 1 on F type characteristic, and they parameterize it with a white noise floor level voltage and a corner frequency. And if you do that, then you've got the whole thing covered. Surprise, surprise. Likewise with current. And as chance would have it, those corner frequencies are never the same. This is 2.7 Hertz here for noise voltage and 140 Hertz for noise current for this particular op-amp. So it's not too convenient. And here's an amplifier scenario where we've got the noiseless amplifier with the noise E bits here, the voltage noise and noise currents for both inputs of the op-amp, both inputs. So it's kind of doubled up, but we presume it's going to be the same as predicted by the characteristic that we just had before. And it's convenient to think of the noises in the resistors as being parallel currents, because then we can imagine that the output of the op-amp is a ground point again. We can imagine it grounded through its equivalent output voltage generator. So this current source and that one are both in parallel with each other in effect. This one down here does its own little bit through that resistor, creating a voltage that gets summed with the op-amp's internal voltage. These currents flow through both resistors. That current flows through, those two currents flow through that resistor, and they will produce voltages. And we can sum all those voltages at the input in this little blob here. So this is the equivalent input voltage that arises from this voltage by itself. Here it is. That current flowing through that resistor. Here it is. This current flowing through those two resistors, one bit going that way, one bit going that way. So we're really thinking of those two resistors in parallel, because we're thinking of this as being grounded internally through the driving voltage source of the op-amp. Here it is. And then there's the thermal noise of the resistors by themselves, yeah, which is 4 kT times R3. It's that one there. And once again, when you've got two resistors in parallel with each other, you can sum on a mean square basis, and that means that we've got 4 kT times R1 parallel R2. It's a mouthful.
So you have to square root the R1 parallel R2 then.
This one over here, over on the right,
Yeah.
well, it's square root of 4 kT R3 or any resistor. Now this is spot noise again. It's spot noise, yeah, because it's only at one particular frequency. And if we would then have to multiply this by a big bandwidth. So we're nearly there though. We're nearly there. Oh, no we're not, damn it. Just when you thought it wasn't getting complicated. Okay. The output noise voltage. Oh, that's bad. What am I better fix that. Excuse me. just when it's getting interesting too. Thomas. Oh, I'm losing the audience. I only made one little mistake, come on. This is where we get back to the expression that we had before that groups things together for a white noise band and the pink noise part with the parameterization of a corner frequency and a white noise level. Yeah? So if you like, everything inside the square brackets here, which has got 1, 2, 3, 4 entries in it, all that stuff is then going to get amplified by, or this is as if it's the spot noise at input multiplied by the bandwidth at input. That, if you like, we can call this E, capital E, N, capital E, subscript, N, I for input. That's what we would see at the input. That just gets amplified by the non-inverting gain of the amplifier to give us the noise at the output. Simple. Nothing to it.
How we know the current?
How do we know the current? This one?
Yeah.
Because...
In the formal slides, it's just a sum from the resistors.
We know that current because they told us in the data sheet. Typical values. So what I'm driving at here is, it might look like it's very complicated, but if you unpack it step by step, it just boils down to this graph and that graph and this graph here, right? So 3 graphs and you got it made.
In the equations much earlier with FB minus FL, it doesn't times it by the pi on 2, and I was just wondering why it's now times by the 1.57 pi.
Okay, that's because they're getting a bit picky here. Been loose before. Take me back to where you think.
I'm in slide 12.
12 is... I've lost my numbers here. Before this one?
That was
Yeah. It's not included there because we've actually said, I have said here, that FH is the noise bandwidth. People get loose with it, yeah? You can either say it's a signal bandwidth, or you can say it's a noise bandwidth. In the question that we posed here, yeah, this one that I just did the solution for, we were predicating that on a stated noise bandwidth. So you're right, if FH is defined as a signal bandwidth, but I could equally have said it's a noise bandwidth. This came before that in explanation, so it would have confounded the issue if I'd introduced this further complication. Yeah? But you're quite right, if that were signal bandwidth before, if that were signal bandwidth, we would need to include it. Non-defined at this stage. Yeah? Perfectly valid. You've got a good point. But I hope you see my point of view there too, because that would be juggling too many balls. I can imagine that the A reasonable man would blow a fuse. A reasonable student would blow a fuse at that stage. Yep. They're complicated, very complicated concepts anyway. I think I said that I was taking you to as far as complicated as it was going to get. That's my promise. This is as complicated as it gets. That's it. Okay, so can you tell me here, for this particular circuit, can you work out for me what the noise bandwidth would be then? Can you see it well enough? I did update this on LMS before I came, so you can refer to that more closely on your personal units. Who will start me off here? What do you reckon? Noise bandwidth. Bandwidth. How do you work out the signal bandwidth? I know you can do it. I know it's on the tip of your tongue. I'll take the wild guess. I'll give you a clue. It's not that hard. What's it going to depend on in this case? Yeah, yeah. Yeah, but what? Yeah, you got it. So what's the signal bandwidth for this one?
I'll figure on the top right.
Yeah.
Maybe 5.
5.
No. Can't see the difference.
You can't? Okay. is my line of reasoning. The gain would be inverting or non-inverting amplifier. And the gain will be then good. And in decibels, that would be roughly 40. Go on the 40 line and we get to, oh yeah, okay. Right, so that's the signal bandwidth. Yes. So if we draw a closed loop, one on feedback factor line here, it will intersect over there. That will be the bandwidth, correct? Because after we get to this point, the ideal closed loop gain can't be achieved anymore, so it will follow that line. So this is the break point for closed loop gain. So that means it's the bandwidth, which we presume from 0, so therefore 100 kilohertz bandwidth, yes? Good? Is that right? Yes? Minor cluster there, couple of, yeah. Do you agree? Right, so the noise bandwidth will be a little bit more than that, yeah? It's first order roll off, therefore we're happy to use ion 2 for the fudge factor, the correction factor. Yes? So we would take that out to about here, I guess. 1.5 would be some there to account for. We can then draw a straight square line here, square block for the noise bandwidth. And believe it or not, all this junk down here's got to fit in that little bit up there. Right. Okay. So it would seem that we know enough then to deal with all that. Correct? Job done? In other words, you can put that value in here. 157 kilohertz can go in this spot, here and here and here. Now, do we need to make it, here's a philosophical question, folks, do we need to make this pi on 2 times, can we make this 100 and, oh God, what am I trying to say? Do we make this 157 kilohertz or just 100 kilohertz? 100 or 150 was my question. 157. We're making this block 157 kilohertz because the FBs are 100 kilohertz, and we presume FL is 0. We can't do that over here, can we? Ooh, oh dear. What are we going to do? We can go to the drama of putting in pi on 2 times 100 kilohertz, or we can just put in 100 kilohertz, and basically the answer to that question is who cares, because it's going to make such a little difference under the log. We'd be more wondering what to put in for FL here, the lowest frequency, and we had that philosophical argument last time, didn't we? And the answer is it matters, but not much. Okay, so can I ask, do you think you're all equipped enough to answer this problem? Some shakes of the head there. You can do it. I know you can. Okay. Can I leave it with you then? Some so-called rules of thumb here from analog devices. For thermal noise in a ordinary old resistor at roughly ordinary room temperature in a 1 Hertz bandwidth, 4 nanovolts RMS. So in 100 Hertz bandwidth, we could just scale that by a factor of 10. So square root of changes proportional to resistance, temperature, square root of resistance, square root of temperature, square root of bandwidth. So any changes, you have to make a factor of 100 change to make a factor of 10 change in the actual value. And you can scale it. Visit the questions on LMS to exercise that point, if you will, if you haven't already. And the major takeaway point is to minimise the noise, minimise the bandwidth. Because that's one thing that we have some control over. We can't usually change the temperature too much. Anyway, okay, enough of that. I've just uploaded this. Notice that Webb's Principles of Biomedical Instrumentation is creeping onto our reading list now. There are 3 copies in the bookshop still. And since people want me to work from a book, that's as I understand it from responses to the staff-student liaison group, then I'm going to do that, largely. A couple of other references here, well, actually bibliography, as I explained, are things that you can go and have a look at if interested. Any questions? Yes, sir.
What would you choose for FAR? Because we have a long divide by shouldn't be 1 or 0. We just raise a log scale graph.
You're talking about FL. Okay, the question was FL here. What are you going to put into that? There was the suggestion from last time, the maximum IC idea. Well, it works, and as you can see here, it makes very little difference if you use 100 or you use the age of the universe, factor of 3 difference. So the main thing is you can't put 0 in because the log won't work, and log with infinity won't work. Put your birthday in. No, I don't mean to be facetious here. Look, strictly speaking, in an experimental environment, you would use the time taken to do the experiment, the time of the observation. Yes. Yeah, because that would be that's the limitation of the lowest frequency. Now, this glib thing from Maxim was basically as I said last time, the longest frequency we can really conceive of is something that started at the beginning of time and has now finished one cycle, yeah? I liked it. I thought that was really good, personally. Any other really good questions? What's the what? That's an arbitrary factor that comes about from, it's FCE there gets abbreviated to this one. It comes about from that. Yeah? It's just a process factor, because what this is all about is it's thought that in devices the 1-on-F process that does that for you guys, don't keep forgetting which direction I'm looking in, that is due to device imperfections, yeah, surface effects and so on. Okay? No. No, K is just a arbitrary factor. What it means is, look, let's say you get this kind of behaviour occurring with devices. One device might have a slope like that. One might have a slope that's parallel to it but a little bit further over. Yeah? Based on production spread, things might change. You might have one that's a little bit better, that has a profile that goes down, further down like that. Yes? Just imagine it's a device imperfection fudge factor. Yeah? Yeah, gradient, if you like. It's a constant for any given device.
We would be given that value, wouldn't we?
No, because the mechanics of all this say that if we equate that noise level where the white noise and, yes, the white noise part and the 1-on-F noise part are equal, then we can eliminate that K. Yes?
Yeah. In the sense of the two noise profiles that intersect,
Yeah.
you can cancel that.
Yep. And that frequency where they intersect, we'll call it the corner frequency. And blow me down, the manufacturers provide us with that if we're good. Yeah? Or we have to figure it out ourselves otherwise. Yeah? But if they have good op-amps that are good in that category of low-end behaviour, they will definitely advertise the corner frequency for you. The index of a good quality low noise amplifier is a low corner frequency and a low white noise floor. Yep. Sweet. Okay. Shall we convene another time? Good. See you tomorrow. And we'll go through the test papers with you individually. That one?
It was with the 3 graphs. You were giving me.
Yeah, you're talking about bandwidth of the signal. So like my reasoning is, what gives you the frequency response here, voltage gain, versus the frequency. So I said the half power point is max gain divided by root 2. And so I got somewhere in 90, cross over it, and go down to somewhere around, maybe 500 hertz.
Run that by me again.
So I said half power point of this is going to be max gain divided by root 2. So that's like basically saying max gain times 0.707.
Yeah.
So that's approximately like 90-ish.
No.
No.
Because the gain is dependent on these resistors. Closed loop gain.
But it's giving us the gain here. Surely.
That's the voltage gain of that, not that with the resistor. We're talking about the amplifier.
Oh, that's not voltage gain.
That's the voltage gain of the op amp itself, the open loop gain, in other words.
Okay. Right.
Well, I didn't make that clear, but this is what you get from a manufacturer through typical.
Yeah, that makes more sense.
I don't know what
so
TPC is meant to mean, but
so what you actually did was you got the overall gain of this,
correct.
and then what?
I noticed it was 10k over 100 ohms,
Yep.
so that means RF over RI plus 1,
Yes.
would be 101. Rendered that into decibels, 40 dBs. Go on the 40 dB line across here, 100 kilohertz.
And that's
That's the signal bandwidth.
yeah.
Yep.
That's like one particular frequency, like range 40 kilohertz. How does that relate to?
No, it's 40.
Well, it's like the ratio of 100.
It means that for any signal up to 100 kilohertz, the output will be 100 times the input, 101 times the input.
Okay. And anything above that?
Above that's going to be scaled down progressively.
Okay. Cool.
Yep.
Yeah.
Well, in actual fact, it'll be 3 dBs down at 100 kilohertz.
Fair.
Yeah.
Alright.
And what that means is that one decade below it will be 1 dB down, but we don't.
Yeah.
Thanks for that. Yes, sir.
You said a little bit later that this F subscript
Yep.
B. I was just wondering how this, like,
Did I say B?
yeah, it's F subscript B. I was wondering why that's.
What did I say? When did I say?
No, I see, well, later on the slides. I don't really remember which slide. Yeah, that one.
Okay.
What's that FB? If, in terms of this, where do I find the FB?
Yeah, I didn't notice it. But it's FB will be the
100K as well.
if he's no, that's 100k in this particular case, 100k
Okay.
because it's not adjusted. The adjustments here.
You do the adjustment, yeah.
Yeah, that's an unadjusted. FB is the unadjusted. That's the signal bandwidth. In other words.
And then FL would be whatever we, this very small number, whatever we
Correct.
decide.
Yeah.
So they're
The
kind of
classic arch.
Yeah. If it's a DC amplifier, then FL is 0. But you can't use 0 in the first term because
Yeah,
it won't work.
yeah. So you just do a very, very small number.
Is D read from the voltage graph? Like just
Yes,
E in?
that's the white noise level.
Yeah. And how about I? Because there's two I values, one
Yeah,
for the positive.
you-
Are they both equal?
We take them as equal.
Okay.
Obviously they can't be, but what have we got? I mean, the manufacturers never differentiate.
Yeah.
And this is going to be typical values anyway. We can penetrate to the nth degree and 10 decimal places, but that's a silly thing to do because it's not worthy of the problem. We typically just need a ballpark value.
So that E and value is the white noise.
Correct.
The graphs.
What we call the white noise law.
Which is where is the picture of?
The
Plateau line.
What?
Isn't that the book? The plateau?
Plateau.
Plateau.
You call it a plateau line, okay. I haven't heard it, but... Oh, that's all right. No, that's fine. Fine by me.
So which line is the white one? Is that horizontal one?
The horizontal one.
Alright, so it's 3 to get the voltage noise. That's voltage for current. Whatever it was.
Stop.
Oh, current reading it, but the white noise, that's that. And then that's the, go to switch back now.
Thank you.
And the other one is, that's this E.
Oh, it's up there.
Go back to the slide. So then that's this E and that's the white noise. That term there. Yeah?
Is the white noise squared or not squared?
Square.
Sorry? It's either. It depends on how it's presented to you. You just have to keep an eye out and see.
So you refer to the units.
Yes, that's it. Yeah. But
And overall
the squared form is it's ready to combine with other ones because you always
Some squares.
yes. Right. So the way to amalgamate different noise sources has the sum of squares. So if it's already in the squared form, that is to say it's a power, then you can add power.
So as for this figure,
Yeah.
to give you
Yes.
square root. So it's the, you can get the value.
That's the n, not en squared.
Okay.
Yes? And there's a difference between the small e and the big E. The big E has got bandwidth associated with it already. Bandwidth's incorporated. So it's something you can actually measure, whereas the small e or the small I is infinitesimally small, just a paper width.
Yeah, just
So then he's pipe noise.
Okay.
Okay. Give me them
The graph.
graph again. Yeah. Yeah, it's like the paper width here.
So you do the
That's the
we got this spot point. We classify the bandwidth and then we get the something else power. Then you can classify the gain and get the something
That's
else.
it. Well, if it's
If you go back to the previous slide,
either way, at the input or output, if you don't define the bandwidth,